Good morning, everyone. I'm Subarna Kole, and I'll be talking about bipolar membranes today, specifically the thermodynamics and kinetics for water splitting in a micropatterned bipolar membrane. So, what is a bipolar membrane? A bipolar membrane or BPM consists of laminated sheets of cation exchange membrane or CEM and an anion exchange membrane or AEM with an intimate interface, and the dissociation of water can take place at the interface of the BPM. Some of the major applications of bipolar membranes are production of acids and bases from their respective salts by a process known as BPM electrodialysis. It can be used to produce mineral acids and bases as well as organic acids. Some other applications of bipolar membranes include photoelectrochemical water splitting and energy applications like maintaining pH gradient across a fuel cell and CO2 electrolysis to value-added components like methane or formic acid. Let's talk about the polarization behavior of a BPM placed in an aqueous salt solution under reverse bias. So initially at low voltages, uh, so here the voltage and current density follows a linear trend. As we increase the voltage, there is a gradual increase in the current density. And this regime of the polarization curve is controlled by transport of coions in the solution, and it's kinetically limited. This process continues until the limiting current density or I lim 1 is reached, and at that point the current density flatlines, and it continues until the voltage of 0.83 volts, which is the dissociation potential for water. At 0.83 volts, there is a sudden increase in the current density, and this part of the curve is controlled by mixed control, which means that it has both transport and kinetic limitations. Finally, the pole curve is characterized by the appearance of a limiting current density 2 at extremely high values of voltages and current densities, and this part is limited by diffusion or transport of water molecules to the BPM interface. Most of the studies that look at improving the bipolar membrane performance are based on improving the membrane chemistries of the AEM and CEM or the catalyst used at the interfacial area. But there are very few studies that have looked at the interfacial design of the BPM. In this work, I have prepared micropatterned bipolar membranes, and uh, I have calculated the scaling relationship between the onset potential and current density of the interfacial area of oppositely charged groups in the bipolar junction region. The effect of catalyst and processing methods are also examined in this study. A soft lithography approach is used to fabricate the micropatterned bipolar membranes. So in the first step, a silicon master is made via photolithography, and PDMS melt is poured on top of this silicon master. After that, the PDMS melt is allowed to dry and it is peeled off to obtain the submaster. The ionomer solution of the CM is casted on the PDMS mold on the pattern side, and it's allowed to dry in an oven and peeled off to obtain the cation exchange membrane with a patterned surface. A thin layer of aluminum hydroxide suspension in water is spray painted on the patterned side and allowed to dry. This acts as the catalyst layer. Finally, the AEM and CM with catalyst layer are hot pressed together at high pressure and temperature, and solvent annealed in nitrogen and butanone vapor mixture. With this process, it's possible to obtain bipolar membranes with a number of different interfacial area values. Also, one advantage of using the reusable PDMS molds is that they are compatible with a number of both membrane chemistries and a number of different solvents. In the previous work performed by Peter Pintaro and his research group, they looked at the performance of a planar junction bipolar membrane with respect to a 3D electrospun bipolar membrane. However, the difference between Pintaro group's work and my work is that I have tried to systematically vary the interfacial area of the bipolar membrane junction region and find out the scaling relationship between different parameters of performance in a bipolar membrane. The anion exchange membrane and cation exchange membrane reaction schemes used in my work are listed below. The AEM is made by QAPSF or quaternary ammonium polysulfone, obtained by the Friedel-Crafts reaction of polysulfone, followed by addition of 1-methylpyrrolidone to obtain QAPSF. For preparing the cation exchange membrane, I have used PEEK and reacted it with sulfuric acid, and it's ion exchanged with sodium hydroxide solution to obtain sulfonated polyether ether ketone. For testing the bipolar membrane performance, a 4-point cell setup is used. It consists of two different compartments filled with 1 molar potassium nitrate solution, and it is separated by a bipolar membrane. Uh, two, uh, two electrodes, working and counter electrodes, are used on either side, and they're made out of platinum iridium mesh. Also, silver chloride reference electrodes are used on either side of the bipolar membrane in order to measure the potential difference across the BPM. Um, so chronoamperometry experiments are run using a potentiostat, and the various conditions are listed in this table below. This slide lists some of the individual AEM and CEM electrochemical properties of the SPEAK and QAPSF used in this work. Now moving on to the results. First of all, the effect of catalyst and solvent annealing on BPM performance was studied. So it's clear from this figure that solvent annealing and use of a catalyst improves the bipolar membrane performance in terms of current density as well as the onset potential for water dissociation. The uh, bipolar membranes made by me have slightly lower current density, but they also have lower values of crossover current uh, with respect to the Fumasep bipolar membrane, which is a commercial membrane that I've used to compare the results of my BPMs. Also, it was found out that catalyst loading does not affect the polarization behavior of bipolar membranes. Next, BPMs with normalized interfacial areas with respect to a flat interfacial area bipolar membrane was studied. So the bipolar membrane that had a flat interfacial area was assigned a normalized interfacial area or NIA of 1, and the resulting interfacial areas of all the other membranes were calculated. So BPMs with a higher NIA have a higher value of interfacial area due to smaller feature sizes. This graph shows the current density at 2 volts and the onset potential for water splitting, which is calculated from the previous graph. So it is obvious that there is an improvement in BPM performance as we reduce the feature size and increase the normalized area. There is a 250 millivolt reduction in water splitting onset potential on enhancing the interfacial area by 2. There was also a 10 to 15% improvement in current density when enhancing the interfacial area with the same factor. In this plot, the onset over potential for water dissociation as a function of local electric field for different NIAs as well as different membrane chemistries of BPMs is plotted. So we can see that as we increase the feature sizes, as we reduce the feature sizes and the interfacial area increases, there is a decrease in onset over potential. This can be explained by the Poisson-Boltzmann equation. So at the interface of a bipolar membrane, when the interfacial area is larger, you have a larger density of fixed charges. This leads to a higher value of local electric field at the junction region, leading to a lower overpotential for water dissociation. Finally, the effect of membrane chemistry on BPM performance was also studied. Apart from the SPEAK QAPSF bipolar membrane, I also prepared SPEAK Orion BPM. Orion is simply an alkaline stable AEM that was purchased commercially. Apart from that, I also made an all perfluorinated Nafion and PFAEM bipolar membrane. So the results show that SPEAK Orion bipolar membrane performed the best in terms of lower onset potential, leakage current density, as well as it has higher overall current density. There is a significant almost 250 millivolt reduction in onset potential for the SPEAK Orion bipolar membranes as compared to the commercial FBM Fumasep membranes. So the main conclusions of this work is that increasing the interfacial area in the bipolar junction region helps in reducing the onset potential for water dissociation due to the larger concentration of bipolar junctions. There is also a slight improvement in current density when the interfacial areas are increased. So my future work will mainly focus on making even smaller feature sizes of bipolar membranes using optical lithography as low as 1 micron. I will also try to make nano bipolar junctions using blocopolymer lithography. Finally, I would like to acknowledge and thank my advisor, Dr. Chris Argus, as well as my fellow lab mates. I would also like to thank my sponsors, NSF and NREL, for supporting this research. And if you have any questions, feel free to contact me here or send me an email. Thank you.